yesterday, so you all know about his extensive CV. I just, in the context of this talk, I wanted to mention that he is also the principal investigator of the European Research Council Advanced Grant Math Card, which is focusing on the cardiovascular system and mathematical modeling of cardiovascular system. That relates to the topic of today, modeling complexity reduction in PDEs for multiphysics. So
thank you. I'd like to start with some basic definition. I guess this is kind of obvious synopsis, but nonetheless, let me remind you what I'm mean by modeling here. Well, modeling means using equations to describe processes. Could be natural, physical, biological, industrial processes, social processes. Multiphysics is a very widely used word today, and part of my talk would be on multiphysics, at some extent. So what is multiphysics? Well, the name explains the meaning, basically. We talk about multiphysics in terms of modeling when we are using models that are made by different constituents, different ingredients, which are typically represented by different kind of partial differential equations. You want to couple fluids and solids. You want to couple waves and the formation of soils and many others. What is a multi-scale problem? Another very used and perhaps abused word these days. Multi-scale problem is a problem in which the components of the solution components, have multiple features, a variety of features at different scales, scales of space and scales of time. For instance, you have different levels of description in material science. You are considering dynamical systems that are evolving. That's another example, in different time intervals and coexistence of different spatial gradients, for instance, for fluid dynamics. Again, we want to combine different geometrical features at different scales, different spatial scales, and so on and so forth. What is computational complexity? Well, I mean, this lecture is also on the use of reduction techniques for complexity, with the aim of reducing the complexity. So computational complexity is the amount of computational resources that are necessary to solve a given problem, and typically referred to CPU, time, memory storage, especially in parallel computational environments. And very often you have to end up with solving your problem in parallel computational environments because of the size of the problem. It might become very unaffordable or even prohibitive when you are solving multiphysics and multi-scale problems. This is especially the case if you are interested in not only solving a given problem at a given time and once for all, but when you are interested in what is called the many queries. For instance, in control optimization and the solution inverse problems, you have to solve the same state equation very many times. Especially if you, even more, if you want to solve real time, problems in real time. In this case, you actually need to reduce the complexity of the problem, otherwise you'll never be able to produce solutions in real time. Now, what should we do from the computational side? Well, we aim at improving the performance of our computational models by using reduced order models that reduce the complexity in many different ways. And hopefully this should be combined with, whenever possible, with the so-called offline-online paradigm, which means that heavy computation ought to be performed offline before starting the whole process, and much lighter computations, those depending on the parameters that change, can be left to be solved online. Of course, you need to have a solver which is almost real-time online, or in any case very efficient online, and you don't really care in this perspective about the amount of work that is necessary offline. All right. Yesterday I've been lecturing on introduction to domain decomposition, and today I would like you to see this under a more, let's say, broader perspective. Here is a way to represent this generalization. What we have been talking about yesterday is basically this first part of the picture. We can call it homogeneous domain decomposition. We have to solve a problem in a given computational domain, 1D, 2D, 3D, and the problem is governed by a certain differential operator that we call L. It could be linear or non-linear. Here it is linear, but does not really matter. So you have to solve the problem, let's say LU equal to F everywhere, and then you have to split it into two different components, solving the same problem in omega 1 and then in omega 2, and then using some coupling conditions of gamma. We call these interface conditions yesterday. And you might remember that for the Laplace equation, these are continuity of U and the continuity of a normal derivative of U. Of course, you can generalize it to many subdomains, and the many subdomains can be generated not artificially, but starting from a given grid, like in this case. So we generate a grid. This is a double ellipsoid, which describes a simplified ventricle of the heart. So you have a three-dimensional domain, you grid it, and then once you have your grid in place, you can call one of these subdomain partitioners that provides you with splitting into subdomains. See, there are those with different colors, and these subdomains can be either connected or disconnected. It is not really an issue, and you see that their form is arbitrary because it's just the union of tetrahedra in this case, and the purpose is to have balanced splitting, in the sense that the number of vertices of the tetrahedra in each subdomain should be the same, roughly speaking. So the amount of work per subdomain should be the same. So this is the classical domain decomposition approach. Here, the goal is to go parallel. So trying to solve the problem in a parallel way and taking advantage of the splitting. And yesterday you have seen two basic alternatives. One is using non-overlapping domains, like in this case. We call this sure paradigm, and the other is using overlapping subdomains. So you can start from this partition and then generally enlarging every subdomain to create an overlapping area, an overlapping, say, volume in this case. And this approach is the one leading to the so-called Schwarz methods. This is the type of generalization that I'm going to address in my talk. One is multiphysics. Multiphysics means that, multiphysics can be represented or simplified conceptually by saying that you have one domain split into subdomains, and on every subdomain you have a different type of partial differential equation. This time you have L1 in omega 1 and L2 in omega 2, instead of having the same L everywhere. Plus suitable condition of coupling at the interface. The other alternative is to have what is called geometrical multiscale. What is geometrical multiscale? Well, you see, you have a computational domain now, omega 1, that is coupled with another computational domain, which is, for instance, one dimension. So you have 2D or 3D coupled with 1D. All right? Now, the boundary, the interface is reduced to a single point, which makes things very complicated mathematically. Now, often this is not the reality. The reality is 3D. For instance, you have a three-dimensional object here, but in some part of the domain you simplify it by using a 1D for specific reason that we'll see later on. So we can call this a sequential multiscale. And this is another multiscale, geometric multiscale, which is embedded, which means that we are solving, assume that this is a porous medium, and you have fracture, right? Now the fracture can be described artificially by one-dimensional model, just if it were a one-dimensional channel. So in this case you have a 3D with a 3D and with a 1D domain. So it's still a subdomain decomposition that again is very special because the equation that you have in this external domain is different, much different than the one that you have in the internal domain. So not only the partial differential equation are different, but the equations themselves have a different mathematical meaning, physical. So it's really a matter of combining different kind of objects mathematically through an interface which could be either a point or a one-dimensional manifold set. And then at the end, if time will permit, I will also make comments on the way to use reduced basis method to solve parameterized partial differential equations. And the parameterization can, for instance, be related with the physical parameters of the problem or to the geometrical way you represent your boundary. Okay, this is more or less the picture. So it's a kind of generalization, abstraction of domain decomposition methods, which is, however, strongly driven by the physical problem which is behind that we ought to solve. All right, I talk about multiphysics and multiscale. And before going to mathematics, I would like to mention three different examples, completely different nature. One is geodynamics, the other is from fluid, and the third one is from life sciences. They, of course, have a completely different type of taste and feature, mathematical feature. The first one referred to wave propagation, wave induced by, for instance, by earthquakes. Now, seismic waves propagate vibrations, so they carry energy, and they can, of course, create, induce strong damages. Here you see two completely different kind of phenomena. You have waves propagating in the water, and here you have waves propagating on the ground. This is a seismogram. There are two different basic waves in seismic propagation. You have compressional waves that are called primary, and transverse waves that are called secondary. And besides, you have other waves, but these are those carrying the most important part of energy. And they travel at different speed, and they carry different kind of energy. Just to give you a picture, P waves, which are compressional waves, in this case the ground is vibrating in the direction the wave is propagating. So assume that the center of the earthquake is somewhere there under the ground, and then you see that the ground motion is occurring this way, and this is the P wave component of the shaping, and at the same time you have S waves. They create a ground motion in this transversal direction with respect to the wave direction, and the two waves behave differently physically and also, say, in terms of velocity. The P waves propagate through all kinds of media, while the S waves propagate only through solid media. So in particular, those propagate also in the water. The classical propagation wave is the let's say, propagation wave velocity is, in this case, is called CP, in that case, it's called CS. They are represented in terms of the Young and Poisson moduli of the media, as well as the density. And as you see here, the P waves are typically faster than the S waves. However, most of the damage is produced by earthquake is the result of the strong shaking caused, shaking of the ground caused by S waves, the transverse waves. The equations are, I would say, relatively simple mathematically speaking, because these are, it could be linear or non-linear depending on the rheology of the ground, but even in the, let's say, in simplest case, you take linear equation, these are the elastodynamic equation. We look for u, which is the displacement in 3 directions, x, y, and z, and u undergoes an equation of this time, which is a hyperbolic equation. Rho is the density, this is the second derivative in time, minus the divergence of sigma of u, and sigma is the stress tensor, plus some, say, inertia terms that are due to friction, basically. And this is equal to the external sources, besides the boundary conditions and initial conditions. So using displacement, the stress tensor is the symmetric part of the gradient, and sigma of u, which appears here, is a combination of, well, let's say, d time epsilon of u, the stress tensor. And the rho is the material density, lambda and u as the Lamé, in this specific case, the Lamé elastic coefficients, and these are viscous forces. So this is the equation. Nothing particularly difficult from the, I would say, analytical viewpoint. However, the difficulty is that you may have a very strong heterogeneity in the material, and on the other side, from the computational viewpoint, you may have a phenomenon that occurs on a large scale, spatial scale, order of several kilometers, and also you may have problems of say, multi-scaled in time, as we shall see. Here is an example. This is a bridge, an old bridge in the northern part of Italy, and this is a simulation. So this is not a real earthquake. The simulation is multiplied by 5. The deformation is multiplied by 5. So here we are solving the elastodynamic equation on the ground and also on the solid material, and of course you are coupling the different domains, so we have different subdomains here that play, and we take it, we take the evolution in time of this. Now, the difficult part here, besides the multi-scale phenomena that I mentioned before, is that when you solve the elastodynamic equation, you need to reduce the errors, which have basically 2 important components. One is the dissipation, and the other is the phase error. Dissipation error and the phase error. Dissipation means that you want to somehow conserve the energy, so to use methods that are not too dissipative. If you would use, for instance, implicit tolerant to advancing time, it would be extremely dissipative. And the second one is dispersion. Dispersion means that the dispersion error is the one that is due to the fact that you are propagating your waves, your wavefront that propagates with a speed which is the numerical speed and could be very different than the physical speed. So if this error is big, we call this dispersion error or phase error, and to reduce this phase error, you need typically to use high order methods in space and hopefully also in time, certainly in space. That's why you have to, well, I mean, we do use spectral element method, which are high order method, or in order so that we at least 4 in every element, in order to make sure the dispersion error is kept under control. This is a more realistic application because we use real data. This is an earthquake that took place 2 years ago in New Zealand, Christchurch, and this is the central business district after the earthquake. And there we had a real seismogram to measure the whole thing. This is to give you a picture of the numerical computational domain. This is the actual computational domain is 20 kilometers by, this is 30 kilometers by 30 kilometers. So it's a very big area in which we want to solve our problem. We have to propagate our waves, and we have to reduce this dispersion error, otherwise wave will propagate with a completely fake speed. And then we want to have a very detailed description in this area, which is the central district. And this is, you see, order 1 kilometer by 1 kilometer by, say, a few hundred meters on the vertical. And this is the simulation. You have the wave that is propagating. The colors refer to the wave, to the velocity of the waves. You see the central district here with the different buildings. This is a top view, and you see, of course, the scale goes from blue to red. Red is the highest velocity, and blue is the lowest velocity. And this is a three-dimensional view. So every building has been represented by, say, a solid model. And so we are propagating our waves on the ground and on different buildings. And you see the wave, they oscillate. Now the factor of multiplication is 20, so it's not that realistic, but it's just there for practical purposes. But in this case, this is indeed the simulation that we made on the basis of the initial condition and boundary condition that were available due to the presence of the seismogram. So this is realistic earthquakes, and all these are important simulation because you can, for instance, see the amount of energy that is trapped among the different buildings and the energy that is released. So you hope most of the energy will be released afterwards, because otherwise, damages should be extremely important. So here, please notice that you have a double scale in space and time because of the necessity of simulating what's going on a map, which is quite refined, like the one of the central district. And of course, you have also different time waves, temporal scales, because you want to simulate not only the propagation of S and P waves on the big environment, but also the way these waves are interacting non-linearly between the different buildings. So we need a much finer time step for the buildings, building interaction. This is the second example, completely different one. It's the art engineering. Now this time we want to simulate what's going on when you consider, say, sailing yacht. And as you can see, immediately you have two basic components, and actually three basic components. One is air, the second is water, and the third is the free surface. Okay? And here are the equations for the water and the air for the fluid part. So these are Navier-Stokes equations. Take this one, for instance. So for those who are not used to work with Navier-Stokes equations, these are conservation equations. The first one enforces the conservation of momentum. The second one is the conservation of mass. There are two basic variables. One is u, which is the velocity in the water, uw, velocity in the water. So you have three components, x, y, and z. The second unknown is p, pressure, and then you have a given density of the water, rho w, and the rest is known. And here is gravity, in case you want to consider the gravity as a source term. So these are the Navier-Stokes equations. The same equations are used in the air. It's a different kind of fluid. The diversity is accounted for by this rho A, the density of air, and the density of water is a factor of 1,000, roughly speaking, one or the other. And then you have interface conditions. What kind of interface? What is the interface? Well, it's a physical interface. It's not a mathematical interface as the one that you have seen yesterday. It's a physical interface, and is wave water surface, say. And here you have the continuity of the velocities and the continuity of the normal stresses up to the surface tension, if you want to account for the surface tension. In that case, it's not that random, so you can forget it, the surface tension, and you have the continuity of the normal stresses. Normal stresses means a combination between the normal derivative of the velocity field and the pressure. Alright, you have a dynamic and the kinematic condition that you force on the interface. So these are the the fluid equations, and the main remark to make here is that the fluid is turbulent, and this should not be the case in the cardiovascular system that we'll address at a later stage. The flow is turbulent, is unsteady and 3D. You have vorticity and the coherent structures which stretch and increase the turbulence intensity. You have different scales, which is typical of turbulent flows, and you have high Reynolds numbers. The right numerical simulation be in this type of geometrical context unaffordable. So that's why typically computational physicists and engineers use turbulence models. So you do not attempt to resolve all possible scales, rather you disregard some scales and you just try to simulate their effect on those scales that you are actually considering. And there are many different types of models. I'm not expert at all in this. I'm sure that in this room there are people much more expert than I am. But these are possible models that can be used, and this is actually the model that we have used in our simulation. We use this SST model, which is based on K omega average equations. We have an equation for the turbulent kinetic energy. We have an equation for the dissipation rate of the turbulent energy. So one is K, the other is omega. Now they look very complicated indeed. They can both be regarded as being nonlinear advection, diffusion, and reaction equations. You have diffusion terms, second order derivatives. You have advection term or transport terms, and then you have production and destruction terms. So they both have the same kind of mathematical structure, and they are indeed, well, I don't have the slide here, I forgot to show it, but indeed we have other equations that supplement the Navier-Stokes equations, and they are there to predict the position of the transition between laminar and turbulent flow. We have two additional equations that simulate the transition between laminarity and turbulence. So this is the old system. We have the Navier-Stokes equations plus these two equations plus two further equations. So all in all, you have three equations for the momentum, the conservation of momentum, one equation for the conservation of mass, and then you have two equations plus two more equations, so you have 8 equations, 8 partial differential equations, all combined together that you have. Yeah.
And how about the structures or the solid?
I will comment on that later on. So this is only the fluid part. Now here we are considering the solid as being rigid, so it does not deform. So we give the shape of the solid, and then we solve the fluid around.
Okay, and so then it's different from solid structure interaction.
Yes, then we'll address also the solid structure interaction. This is pure fluid simulation. So. And actually, to make an historical comment, we've been involved with the Alinghi stuff, which is the boat, the Swiss boat, that won in 2003, and this is the simulation of 2003. So in 2003, we only cared about the fluid part. We're not able to do the fluid structure interaction. 2007 also accounted for the interaction with the cells, and I will address it later on. But this is the very original award that we made now 10 years ago, so long ago. So here is just the detail of the solution. This is the bulb, and this is the keel. These are the winglets, and this is the rudder. This is the detail of the solution. And this is the free surface. This is the hull, the Alinghi hull in 2003, and here is the way the free surface behaved around this hull. And of course, simulating the free surface is important because, in particular, we see what is the wet part of the boat, of the hull. And here is not yet the fluid structure interaction. This is just undeformed cells, and this is the flow field around the cells. So these are only flow equations which are solved, and this is same kind of well. This is the Alinghi 2007. So this is Swiss 100, the one that won in 2007, and this is the catamaran in Multiphysics in 2010, and it was defeated by Oracle. And, but this is a completely different type of physics because you don't have appendages anymore. Multi-hull, and you know that multi-hull flies. You only have one hull in the water, the other is in the air, and the sizes are completely different. This is a 56 meters tall mast, and the speed is also very different. I mean, this can go up to 3 times the speed of the wind, say. Now, this is the detail on the grid for the water part. We are using here finite volume approximation for the water, for the simulation in the water. And you see we're using structure grids, but they're generated by multi-blocks. So again, we have a multi-domain structure. You have big blocks, and every big block is actually a domain, and we use Schwartz method to solve the problem in every subdomain. Here is, in fact, the grid that we use for the wind sail interaction. The wind does move. This is an top view of the sail, of the main sail. 2007. So the grid is moving. You see there is a kind of cylinder, which is a virtual cylinder, in which the grid is moving, and you are using an unstructured grid. This is made by tetrahedra. And then in the far field, we are using a structured grid. So this is somehow rotating. The internal cylinder is rotating. The external grid is kept fixed. So in particular, you need to accommodate the grid interaction on this virtual interface, and also, which is even more important, to accommodate the grid interaction between the cells, which is now simulated. So we have equations for the cell and the simulation and the equations for the fluid. So there are basically 2 components of difficulty here on top of the partial differential equation. One is how to account for the grid motion, and the second one is how to transfer information between 2 grids which are completely non-conforming one another. Right? These are kind of pure geometrical aspects that are on top of the story. And the difficulty is that, well, first of all, you have to couple different solvers. Sometimes these solvers are generated by different people. This was the case in our computation because the solver for the sail was generated by North Sail, that was proprietary and working for Alinghi, but not only for Alinghi. So in particular, it was a confidentiality aspect, and we have never been able to use that code. We are only allowed to use the output of that code and to give input to that code the information coming from the fluid. So you only have to work on the interface, right? On the computational interface and transfer information. You have to couple different solvers, which is very often the case in practice, because sometimes you have to solve a problem and you want to couple solvers that are generated by different people, and sometimes you are not allowed to enter into the specific into the source. You have large mesh deformation, like in this case, you see. You have great computational cost, and as I said before, you have two features that you have to account for. One is mesh motion, and the other is the intergrid interpolation. You have completely different kind of grades. For instance, in this case, finite volume generated grade, and on the other side, finite element grade, and with no conformity at all at the interface, with different values of the degrees of freedom, because in one case, in finite elements, you have nodal values, in the other case, finite volumes, you have self-centered values. So you have to accommodate all this diversity at the interface. So this is just a sketch representation. You have a fluid and the structure, and of course, the boundaries do not match one another. So one possibility is to use, to generate the grid that is moving at every time step, to use harmonic extension, as we have seen yesterday. This is what is called a plus base, and that's very inefficient because it generates grids that are not regular. Two other options have been used. One is non-conforming grid operator, which is based on the radar basis functions. I will say 2 words at the very end of my talk this morning. And the other, for the Frisch mesh deformation, use the inverse distance weighting. These are two possible options that we use to accommodate, as I said before, completely different kind of grids, and to transfer information from one grid to the other. Now, this is the third application, and this is the one that I will more extensively address, and this is to life sciences, and in particular to the work that we have done about the modeling of the cardiovascular flow. So the object here of our investigation is the circulatory system that is made of millions of small components, actually billions of tiny capillaries, and hundreds of big vessels, big arteries, and big veins, plus one heart. We like to if possible, or whenever possible, to use subject-specific analysis, which means that the data are generated by a specific person. Of course, before going there, you have to make sure that you have a system, a modeling system that is good for the kind of paradigmatic man, right, or patient, and at least in physiological conditions, and then you may want to use it to specialize it to account for the diversity of individuals. So you start from data, hopefully generated by a specific subject, then you need to set up equations, and this is the mathematical model, then you need to solve it, and then ideally we like to go under these two steps, and these two steps are verification and validation. So what is verification? Verification is the property that the numerical solver is indeed capable of converging to the exact solution that you'll never be able to generate. So we have a mathematical model, and then you have its approximation. And verification means that the numerical solution will be stable and convergent to the exact solution that you'll never be able to reproduce. So this is a kind of operation that is internal to mathematics. And validation is more ambitious. We want to show that, we like to show that the numerical solution is capable of representing the reality. And sometimes you have data, other times you do not have data. So this is the most challenging aspect. And then, if these two steps are somehow at some extent passed, then we might be able to address real clinical problems. That's very general, right? It's a kind of general picture that everyone working in life sciences modeling have to somehow undergo through. So again, just to say some make some obvious comments. You start, for instance, in this case, from a 3D magnetic resonance. You want to extract, first of all, slices of contours, and then to create three-dimensional models. And this is the one in which you are going to solve then your problem. Before solving the problem, you have to generate a superficial grid, and then extrude it to get an internal grid. The superficial grid is made of triangles, the internal grid is made of tetrahedra, for instance, and then you're ready to set up your mathematical equations. This is a preliminary aspect. This is a standard simulation of a rigid boundary bifurcation in the carotid artery. The carotid artery is in our neck, and it brings blood to the brain, and through this branch, and to the facial muscle with this other branch. And this is just one systolic and diastolic peak. So this one heartbeat takes about 1 second, and this is the typical form of a physiological, say, profile. You see that it's not like in the Poisson case, because of the pulsatility is not parabolic. It's a deformed parabolic profile, and in particular we remark that near the lateral surfaces you have backward flow, which is physiological. Right? Now, why is this site important? Because it's a preferential site for the formation of plaques, or atherosclerotic plaques, of narrowing, say. That's why people are so interested on solving this problem. Now, before going to the clinical aspect, let me say a few words concerning the way we solve these fluid dynamics equations. Now we have Navier-Stokes equations. These were not the case yesterday. Yesterday we only had basically elliptic equations, scalar equations. This time we have Navier-Stokes. And now we like to have somehow to generalize some of the methods that you have seen yesterday to address the specific cases. And of course, there are many, many different ways. Here is just one of those possible ways. The idea, as I tried to convey yesterday, is to set up suitable preconditions of what? Well, of the algebraic system that you generate after time and space discretization. So you have Navier-Stokes equations, which are an incomplete parabolic system, partial differential equation, discretizing time and then discretizing space. And at every time level, you are left with a linear system, or a nonlinear system, depending upon the way you are discretizing your nonlinearities. Then you need to use preconditioners, because otherwise you'll never be able to solve the problem efficiently. And yesterday I tried to highlight the fact that the preconditioners should be ideally scalable, optimal, robust. Scalability is, repeat it again, scalability is the property of reducing by a factor of m the computational time if you are increasing by a factor of m the number of processors of subdomain, say, in subdomain decomposition. Optimality is independence of the dimension of the problem, so in this case of the grid size. Robustness is in principle the quote indifference to the physical parameters. So in this case, for instance, the Reynolds number, which is a measure of the potential instability of the flow. All right. So we are still in this upper part of the story as yesterday, and here is here is an example. I mean, you know you can discretize Navier-Stokes equation in very different ways. This is perhaps the simplest one. You use an implicit order, first order scheme, not really adequate. In general, we use second order scheme, but it's just for the purpose of for pedagogical purposes. We advance in time from Tn to Tn plus 1, and you see this is the inertial term, the time derivative, this is the viscous term, this is the pressure term, and this is the convective term, u dot gradient of u. And here is semi-implicit because we have un plus 1 here and un there. Then we have the divergence of un plus 1 equal to 0 plus the boundary condition. So this is now a linear system because of the presence of un here. We use P2, P1 finite elements, for instance, and we end up with a saddle point problem of this type. This is a linear system. F is the responsible for the presence of un plus 1 here, Laplacian of un plus 1, and u dot gradient of un plus 1. That's why it depends on un. Then you have B transpose, which is the matrix that represents the gradient. Then you have B, which is the matrix that represents the divergence. And you have a 0 here because in the second equation you don't have pressure. Right? And this is the velocity at time n plus 1 and the pressure at time n plus 1. And this is the right hand side, which depends on the previously computed solution. So if you have any problem with notations or any other question, please don't hesitate to ask. Okay? So this is a classical saddle point form of the system that you generate when you solve Navier-Stokes equations after the linearization, say. As I was saying before, you can use higher order schemes. For instance, Cran-Nicholson coupled with Adam Bashford. In this case, you have slight modification of the equation, but now it's a second order method. You may use something which is even more sophisticated, like this third order backward difference scheme for time derivative and the third order separation for the convection term. You see, the equation becomes a bit more complicated, more involved because you have all these terms here. But the structure of the left-hand side is about the same. You change the coefficients, but the structure, this saddle point structure, is absolutely the same. So, from the point of view of the preconditional setup, there is no basic modification. All right. So to oversimplify, you have a matrix which is F B transpose B Z. Now, perhaps the first remark that can be made is that these matrices can be factorized in many different ways. This is the simplest one, but there are very many others. You see, this is a block LU factorization, like when you have, say, in basic numerical analysis courses, you have a matrix heavy, and which is a priori, full matrix, or in any case, it doesn't have any specific structure, and you split it into an L matrix, which is lower triangular, and a U matrix, which is upper triangular. So L A is equal to L times U, and here is the same story, unless that now you have a blockwise triangular and a lower triangular and lower triangular and upper triangular. You have the identity here, you have BF minus 1, you have FB transpose 0 minus S. Okay? So you have two L, it's an LU factorization, which is fine apart from the presence of two guys, which are very embarrassing here. One is F minus 1, is the inverse of the fluid block, of the velocity block, and this is the Schur complement. Remember yesterday the Schur complement. Now here we have eliminated the velocity and you generate an equation only for the pressure, and this is the matrix form of the pressure equation, and again you see it contains F minus 1. So it's a nice representation, a new representation, however it contains terms that depends on F minus 1. And you'll never be winning of computing the inverse of a matrix, as I was saying yesterday. So somehow you have to simplify this. All right. How do we simplify it? Well, instead of that factorization, we use a different type of factorization. You know that you may have use alternative factorization here. You may use what is called L D U, lower triangular, upper triangular, and diagonal. Okay, there are many ways to get these alternative factorization, and here is one. And actually, this is even more complicated. You see, you have a diagonal, upper triangular, diagonal, diagonal, diagonal. Right? So you have 5 terms. However, 4 out of 5 are diagonal terms, and only one is this one is upper triangular, but you have the identity on the diagonal. Right? So this is a factorization that was proposed by Sylvester Hellman, Kane Watton, then by K. Loggin and Watton. It's called PCD, pressure convection diffusion, because you can generate it by transforming the original equation an equation for the pressure, which is of the convection and diffusion type. But still you have F minus 1. And then you can replace by a precondition of F minus 1. And then in this case you get an approximate inverse of the original matrix. An alternative is based on this Spoliosida factorization. You see, in this case, you have 1, 2, 3, 4, 5, 6. So they're all diagonal, unless for 2, the second one and this one, which are upper triangular and lower triangular, but again with identity on the main diagonal. And an alternative again is based on the so-called simple preconditioner that was introduced in its earlier form long ago by Papankar Spalding, and then it has undergone very many modifications and improvements over the years, but the basic structure you see is still the product of simple shape matrices. Please note that when you see S showing up here or there, these are either the exact Schur complement for the pressure or an approximate Schur complement for the pressure. The exact will be B, F minus 1, B transpose. Here, F is being replaced by a diagonal. So this is very simple to compute. So these can be used as preconditioners for the saddle point form of the equation. And I was saying before that, in fact, you want to remove F minus 1 and A minus 1 in all the terms, and we use hat. When you see the hat, this is an approximation. What is this approximation made of? By domain decomposition precondition. So, just to oversimplify, this is F is the part F is the part of the matrix which is associated with, say, U 1 over delta T minus nu time delta plus UN dot gradient. Right. This is this matrix here is associated with this type of operator, which is a diffusion, convection, and reaction operator. Now, this is a matrix by itself, and assume that to solve this problem, you use a Schwarz precondition. Okay? So we can replace this, formally speaking, by F hat being the Schwarz precondition of this matrix. So we replace it in specific places, and then we have this factorization in which the terms are represented by virtual matrices, which indeed indicates the presence of Schwarz preconditioners. So whenever you find a difficult term, a difficult block, please replace it by a domain decomposition precondition for that specific part. For instance, this AP is the convection diffusion operator for the pressure, which is scalar. Replace it by convection diffusion Schwarz preconditioner, as we've seen. You have similar type of behavior here and there. We call A PCD, approximate, A Yoshida, A simple. Just to denote that every nasty block has been replaced by the efficient precondition. So here you see the way you can play with the precondition that you've seen yesterday as building blocks or more general preconditioners, which are expressed by factorization of matrices. Okay? So the basic idea is a kind of conservation law of the difficulty. Once you know how to solve a simple problem, try to take advantage of that by embedding it into the more general structure. And this embedding is made possible here because of the fact that we are using a factorization of a big matrix. So these are the preconditioners. And all right, this is basically what I said before, that we are using algebraic additive Schwarz, or in such cases, for instance, for the pressure convection diffusion, you use a V-cycle multiple. Why not? I mean, if you have efficient blocks, efficient solver for simple blocks, you can try to embed them into the approximation structure. All right. Here is a simple test case, and then we stop a little while. The simple test case is called the Green-Schultz-Weller benchmark cylinder. We basically compute here the so-called weak scalability. What is the weak scalability? Weak scalability is that if you have a problem and you solve it with one processor, say, then if you double the length, in this case of the cylinder, and you double the number of processors, you should be able to show that ideally it takes exactly the same time. And then you go four times exactly the same time, and so on and so forth. This is the weak scalability. You increase the size of the problem, and meanwhile you increase the dimension, the number of processors. So ideally you should have one. Ideal scalability would be one. Well, it's not that bad. It's larger than one, but say in the order of 10%. So we fail to have exact scalability. You would almost have never exact scalability, but for a little amount. So it's almost weakly scalable, and here's the length in the slope of the curve. It should be ideally flat. It's almost flat. We are comparing these results with those that you would have by using a full Schwarz precondition for the old system. And the Schwarz precondition is not as efficient as this is the algebraic Schwarz. It's not as efficient as these other preconditions. See, these figures are higher than those that you get there. The red part is Schwarz, global Schwarz, while the other parts are, say, factorization plus other preconditions. We use two different platforms. One is the Blugene P of Lausanne. Now we have a Blugene Q, but we used to have Blugene P until the end of last year. And this is the Monte Rosa Cray XC6 in Lugano in Switzerland. And this is another benchmark for weak scalability. You see you have this vessel. Now you start with this size, and then you double the size, and meanwhile we double the number of processors, and then you multiply by 4 the number of the size, and you multiply by 4 the number of processors. And we use two different grids, the fine grid and the coarse grid. And the fine grid is the one in which you actually solve your problem. The coarse grid is the one that you use to generate your two-level Schwarz method. You remember yesterday we have two coarse grid, the coarse component of Schwarz. So here is the way we go. And here again you see the numbers. So the best one is APCD for this specific application. You see these are the ratio, it should be 1 ideally. It's not 1, but it's not that bad. And these are the curves. So the upper one is the Schwartz, global Schwartz, which is much less effective than the local Schwartz or the local multi-grid on the factorized scheme, say. And all right, this shows that it's almost weakly scalable. So if you take this in a quote, almost. Weakly scalable means exactly scalable, so it should be 1.00, which is almost never the case. This is strong scalability. In this case, you just have a problem, and the same problem, and this time we have 35 millions of degrees of freedom for the velocity and 1.5 for the pressure. So all in all is 38 millions of degrees of freedom on the fine grid. Then you have a medium grid and the coarse grid. The coarse grid is really very, very coarse. Now we solve this problem on a certain number of processors, and then increase the number of processors, and we see the way the solution behaves. This is just the detail of the solution, and here are you see this is the number of CPUs, and this one you use the coarse, the medium, and the fine. And of course, you take the most advantage when you use fine grid, right? So ideally, you should go on and using an even finer grid, and the slope will be even smaller. So what is interesting to notice here is that we are comparing two different conditions, the AOCDA and A simple, and in particular, we see here two different curves which refer to different values of the Reynolds standard, 400 and 1000, and we see that the curves are basically the same. Right, which means that the method is quote unquote robust in terms of the Reynolds number. At least at that level, when you don't yet have turbulence, so it's probably still the fluid is still stable. All right, I think it's the right time to stop, and then next hour I will talk about fluid structure interaction. So far, the fluid, we treated only the fluid part, right? The picture and the figures that you have seen are all referred to the solution of the pure Navier-Stokes problem and then given them. All right, this the second part I will comment on the fluid structure interaction. And fluid structure interaction can be regarded as special kind of multiphysics, as I said before. You have two subdomains in which you have fluid on one side and solid on the other side. The point is that we're interested in solving fluid structure interaction, for instance, in arteries, and that the arteries are deforming. So there's two subdomains change in time. And there are several ways to account for this variability. And one possibility is to use what is typically called the ALE frame of reference. ALE means arbitrary Lagrangian Euralian. Why that? Why is this a possible approach? Because, as you know, in general, not always, but in general, one tends to use an Euralian description of the fluid and a Lagrangian description of the solid. So Euralian and Lagrangian. And somehow you have to accommodate the two approaches, which are different, Euralian and Lagrangian. And one possibility is through this arbitrary Lagrangian Euralian. What is the basic idea? The basic idea is that you have a domain at time 0 and you have a domain at time t. For instance, these you can regard it as being the section of an artery. Right? You have an artery, two-dimensional artery, simplified. It's two-dimensional artery. You take a vertical section, and this is the white part is where you have the fluid, which is the blood. The gray part is where you have the solid material, which is the vessel tissue. Okay? And this is the actual situation at time t. Of course, these, the upper and the lower, is a real surface. The vertical ones are virtual surfaces because you want to solve the problem in a limited domain. And then you cut artificially your boundaries or your vessel. What you want to do is to create a map that we call AT, and A stands for arbitrary Lagrangian area, at time t, that is capable of retrieving at time t the computational domain from the original domain. Now the computational domain, as said before, is made by real boundaries, physical boundaries, and artificial boundaries. And the AT has the role of retrieving the specific form from an original form. So if the boundary if the boundaries do not move, then this domain will be equal to this domain. Then AT would be the identity, and this would be the Eulerian representation. Right? You just fix your domain and you want to see what's happening there. If all the boundary will move, then this will be described in terms of the trajectories, and this part of trajectory say. So this would be the Lagrangian presentation, the Lagrangian map. But in this case, it's neither Eulerian nor Lagrangian because, again, because of the combination between physical and virtual boundaries. So it's a kind of in-between. And why we call it ALE? Because you have Lagrangian and Eulerian, as I explained, and then A means arbitrary, because in fact, what you want to describe here is the whole domain, but the whole domain can be obtained through the boundary, and there are several ways to generate the same domain by given boundary. So there is an arbitrarity in that, and this is why we call it arbitrary Lagrangian area. There are many ways to recover a map, which is a two-dimensional map from the boundaries, or a three-dimensional map from the surface. This is the arbitrarities. There is a simple equation that is behind this. It's this identity. You take the derivative of a given quantity according to A tilde, and this is the partial derivative of Q with respect to T, which is the radial derivative plus this extra term, which is W times rate of Q. Rate of Q is the spatial gradient, and W is the rate of deformation of the domain. So W is the time derivative of the map. So you can connect, you can take the derivative along this trajectory, say, in terms of the usual derivative, partial derivative, provided you make this correction. Now, if we apply this idea to this property, this relationship, to this integral, here we have a function f, which is integrated over a domain that changes in time. We know that we have to face with domain that changes in time. And we want to take the total derivative of this quantity here, which is the average of f, say over the domain omega 0 of t. Then you pass this d inside, and you generate df over dt along a tilde plus f times divergence of w. And then you can express this by the help of the previous equality. You can express this in terms of the Eulerian derivative plus this extra term. And this is what you get. You have df over dt plus w gradient of f plus f divergence of w, which means divergence of fw. So this is what you get. And if you use this approach, if you use this simple properties, you can reroute the Navier-Stokes equations in the ALE framework. Before we solved the Navier-Stokes equations in an Eulerian framework, and now you have the same equations in the ALE framework. You see, the continuity equation remains the same. The momentum equation changes because we have replaced du over dt by d over dt by the ALE derivative instead of the Lagrangian derivative, the Eulerian derivative. So we do it in terms of the Jacobian of the map, and So this is the new acceleration term. This is the old term. However, the novelty is the presence of this W that was not there before. What is the W? Is the rate of deformation of the domain. And in fact, the convective velocity, instead of being UF, is UF minus W. Roughly speaking, the price to pay when you replace the Eulerian derivative with the Lagrangian, arbitrary Lagrangian Eulerian derivative is the insertion of this term, which is W here. So you just slightly modify your equation, your convective term. Why do we want to replace the Eulerian derivative with this arbitrary Lagrangian Eulerian derivative? Because if you have, for computational reasons, if we move our domain, the points of the grid will move. If you have to compute a derivative in a given point, time derivative, we should go back and see where this point was at the previous time. And this is a bookkeeping that is quite involved. Instead, with the ALE, the point is always the same because you go to the original point in the original domain, and then you take the derivative always at the same point. So the computation of this term is very simple. For instance, the finite element analysis, but also the finite volume analysis. The price to pay is that you have this extra term W that you inject. It's not such a big price. But you have an extra unknown that you have to compute it every time. So every time you have to compute the time derivative of your AT map. That's the extra cost. Besides, you have an elastodynamic problem for the vessel, for the artery, and this depends. You see, this is not that different from the elastodynamics equation that you have seen for the earthquakes, but of course the rheology is completely different. So the constitutive equations are might be totally different, and the mathematical structure is the same, but the constitutive equations are different. And of course, it depends on whether you are solving, you are considering a healthy artery or an unhealthy artery. The tissue will change dramatically, and you have to account for that. So these are the fluid equations. These are the structure equation, and then you have an interface, which in this case is the endothelin interface, and in the interface you have the matching conditions. And the matching conditions are the kinematic conditions. U should be the same, the velocity should be the same, and the dynamic condition, the stresses should be in equilibrium. So the velocity is the same, means that the velocity of fluid particle should be equal to the rate of deformation of the vessel, which is the time derivative of AT, W, see this W. And here you have that the two forces should be in equilibrium, but one force is expressed in Eulerian terms, the one for Navier-Stokes, the other is in Lagrangian terms. Then you have to make sure that the comparison, the equation is written on the same system of reference, which is the original reference system. That's why you have these at variables everywhere. At means that you are on the reference domain itself. And besides, you have a third equation, which is what can be called the geometry equation, and it is there because the domain is moving in time, and this equation will allow us to compute the rate of deformation of the domain and to plug it into here and there. So you have to compute eta at f. This is, well, first of all, you have to compute the rate of deformation of, you have to compute the deformation of the artery through this equation. Then you extend it to the inner part of the domain, and you get deformation of the fluid domain. You take the time derivative, and you get this W. And the way you extend this is arbitrary. Again, you can go from a trace, a dirichlet trace, to the whole information inside, and you have many different ways to go this way. For instance, you can use the harmonic extension as just seen yesterday. This is just one example. So you have three fields: the geometry, the fluid, and the structure. You have three sets of blue equations, and then you have three sets of red equations that are the coupling conditions. So this is a free structure interaction problem with independent equations coupled through interface conditions. Okay? let me summarize the whole thing, because you can have the same structure for many other free structure interaction problems, not only for vessels or for sails. But the common denominator is that you have fluid problem, the structure problem, the fluid mesh motion, plus the kinematic condition, the dynamic condition, and the geometric condition. So fluid problem, its primary variables are U and P, velocity and pressure, but this also depends on W, which is the rate of deformation, and the deformation of the boundary. Structure problem, the main variable is D, deformation of the boundary, the structure say, and this is fed by U and P from the fluid. Mesh motion, you have the deformation of the boundary, and you have to retrieve the whole deformation of the grid inside. Kinematic condition, U is equal to W, W is D point. Dynamic condition, normal stresses generated by the fluid should equilibrate the normal stresses generated by the structure. Geometric condition, of course, the deformation of the artery of the structure at the interface is equal to the deformation of the fluid domain. So eta is equal to E. So this is the three-field fluid structure couple problem that we may have many other contexts as well. So, all right. You have different possible sources of nonlinearity. One is due to the fluid model. We use Navier-Stokes, so you know that the convection term is nonlinear. Then the structure can be either linear or nonlinear depending upon the material properties, and the geometry is changing because you have a moving domain and it moves according to an unknown law, because this is part of the solution process. So geometry is also nonlinear. So you have three sources of nonlinearity, basically. Now you have to use time and space discretization. And when you advance in time, you can either use full implicit algorithms or a convective explicit, in which this Navier-Stokes term is treated explicitly, as you've seen before. Or you can also use an explicit geometry, which means that when you're solving the problem at time t(n + 1, you may assume that your domain was the same as the time as before, in the previous time. So we are using an explicit approach also for the domain. I mean, I'm not saying that you should use this, I'm saying that this is an option, possible option to generalize your problem. Now, in terms of space discretization, you can use sterilized finite elements or P2, P1 finite elements, P2 for the velocity, P1 for the pressure, and for the ALE map, we represent the ALE map by finite elements, and then you can use P1 ALE map. You can use high order ALE map if you want to use high order methods for discretizing the primary variables. The 1P thesis, we also looked at the use of aspect variable methods for all the variables, including the ALE map. Oh, sorry, this is Italian. Okay, it's not that important. I mean, it's only picture. This is one application. You have seen before that you have the carotid artery, which is here. You have a bifurcation. You may have over the years this is the normal carotid artery, and this is a narrowing. You see the fluid is only through the innermost part, and here is the way it develops from the say healthy level to the very unhealthy, where you have a lot of lipids. In this case, 70% of the lumen is occupied by the presence of this plaque. Of course, you have several ways to repair this. One possibility is just to remove the plaque. One is to insert a stent. The other is just peeling the plaque and then restoring the fluid, the flow part. And here is what you see before and what you see after. This was before the intervention, and this is after the intervention. You see the This was the original plaque. I'm sorry, this was the original lumen, and now it's occupied by the plaque, and then this is completely restored, and of course you see the way the velocity field develops. It's completely different, and in particular the velocity is much smaller, and the fluid is much more stable in the second after the TEA, which is a typical surgery procedure. This is the same kind of model that is used to simulate fluid structure interaction in the ascending aorta. You see the heart is somewhere here. This is the ascending aorta. This is the time after the first heartbeat. Now it's a systolic peak, and then will be a second heartbeat. You see right now you have a second heartbeat and second systolic peak, say. And meanwhile, you see the way the external vessel deforms. So you see the displacement. And this is up to 4 millimeters, the highest, which is fairly big actually, because I mean, this, here the diameter is of the order 1.5 centimeters, and 4 millimeters is considered to be a large deformation. It's hard to be neglected. Of course, there are many simulations in which you can neglect it. Maybe there's still a debate for that, but it's fairly hard. This is just the detail of the mesh. How do we create the mesh? Well, you have the surface mesh, and then for the structure, and then we have the mesh for the fluid. And what you do is typically using few layers for the structure, say 3 to 4 layers, great. And then for the fluid, we use a completely unstructured mesh. However, near the boundary layer, we use quote a boundary layer mesh. We try to reproduce the layers. In order to better accommodate the high tangential, the present boundary layer, so the very high gradients that occur in the normal direction to the boundary layer. This is the layers. These are the layers for the structure. This is to give you an idea of. The way we can accommodate this in terms of domain decomposition. I said an hour ago that our solvers are based on preconditioners that are based on a domain decomposition partitioning of the domain, because we go back to Schwarz, for instance, in this case. And what we do, this is just a pictorial representation of what we do. This is the fluid, and this is the structure, right? These are different solid representation of the fluid and the structure, and this is the actual grid, and this is the actual matrix. So the matrix has this structure, right? This is the fluid structure matrix, the big monolithic matrix that you have to account for, and here is the way we partition our domain into subdomains. Of course, this is done automatically. So the different pieces that you see are, this is one subdomain for the fluid and one subdomain for the structure. Please notice that they are not connected, and they might be completely unrelated, right? You proceed independently, and these are sent to, say, to the first processor. And this is the part of the matrix that is occupied by, is affected by these two terms. Then you have the second processor, which account for different pieces, different components of the domain. It's the red part. And then you have the third, and then you have the fourth, and then you have the fifth, and I think this is the end. No, it's not yet the end, because right now is the end. So in this case, we're using 6 different subdomains, and therefore 6 different processors. I mean, in fact, we use many more, but this is just to represent the idea. And you see, every domain and every processor is actually taking care of different pieces of the fluid domain and the structural domain. And there's no need for them to be connected. Right. This is made on the pure purpose of having a balanced representation. And these are the different colors, these are the different portions of the matrix that are due to the different subdomains. So this is the way they contribute to the global matrix. All right, this is another application. Now is the flow in the iliac artery. You have the abdominal aorta, you have the common iliac arteries, and then you have the iliac bifurcation here. You go to the internal iliac and the external iliac. And then here is the main branch of the iliac artery. This is the bifurcation, and this is again same kind of representation as before, in which you see the streamline, the straight lines, and the deformation of the external artery. Now it's less important than before because we are in a more distal situation, and the closer you are to the heart, the higher the deformation of the arteries. So in that case, maybe you can also account for a pure fluid simulation without considering the deformation of the vessel, but yet is not completely negligible. You see, is 1.2 millimeters of deformation. Okay, I think we skip this because just to give you an idea of a completely different kind of problem in which you have again free surface and it's a bioreactor and then instability of flow, and you have it coupled with stem cells growth. But this is this is fluid. The free two biphasic fluid because you have water and air, and you have a free surface, and you have deformable vessels. But in this case, it's still ALE, but the motion is induced by reactants. So it's not a fluid structure interaction in the classical sense, because the motion is induced by it. So, all right, this is just let me make perhaps comment on where we stand and where we like to go. And now, of course, when I say where we stand, I'm talking about self and my group. But perhaps some of these considerations are having more general flavor. What we did 10 years ago, just to give you a very simplified vision of what we're doing, actually, what we did 10 years ago, or in the past 10 years, was basically direct simulation of fluid or earthquakes or whatever. Today we're more and more interested. Today actually it was 2012, but because we celebrated 10 years of MOX last year, that's why I have this picture. But the idea is the same, right? It's so coarse that we do not have to change it. Today we are more and more interested in optimization and control, or multi-query analysis, and perhaps tomorrow we'll be more and more interested in solving the inverse problems and parameter identification. And at the same time, I can say that we are more and more changing the deterministic models with non-deterministic models of uncertainty quantification. And we can perhaps oversimplify saying that the models today and in the past were the research was based on modeling, and the research in the future is more and more based on data analysis and data integration, because of the amount of data that we have, which are more and more interesting, realistic, and complex. You need PDE to describe the structural models on surfaces, for example, the brain, on the ventricle, on the heart, right? But you need PD models to describe the data, right? And then once you have the description of data, you can use that for new PD models to describe the phenomenon. So the interplay between data and models is becoming more and more stringent. Now, as I was saying at the beginning of this talk, the computational cost is becoming higher and higher, and the idea very often, especially when you have to face requests from the real world, is to reduce the cost, cut the cost, right? Not only cut the cost of the economy, but cut the cost of the computation, providing solutions which are plausible, not necessarily accurate. I mean, academic solutions should be very accurate. Research-based, academic-based research should provide solutions that are very accurate. Industrial-based research sometimes should provide solutions that are plausible, that are realistic, not necessarily hyper-accurate. And how to cut. And this is my personal view. I mean, in order to cut, you need to learn a lot about the model, a lot about the phenomenon. If you know, the more you know, the better you know how to cut. The more you know on a problem, the better you know how to cut. How to cut the, I'm not saying irrelevant, but the inessential components of the complexity. For instance, solving the fluid in the arterial system on the circulatory system. Now, so far we have seen how to solve a problem in a specific environment in one carotid artery, in the aortic branch, or arch, in the iliac artery. These are a few centimeters of flow problems solved in a three-dimensional domain. But in fact, I mean, the whole flow circulation is connected, and it's a big complex network which comprises one aorta, one vena cava, but you see you have hundreds of arteries of high caliber and many arterioles of smaller caliber and billions of capillaries. And the same for venous and veins. And the Reynolds number is very different. You see, you go from, these are physiological numbers. You go from a few thousand in the main aorta or vena cava up to, you see, 0.002 in the capillaries. So you have a geometric complexity from one side and you have a mathematical complexity or physical complexity from the other side. I mean, the behavior, flow behavior is completely different in the different components. How do you account for this complexity? How can you solve this problem? Of course, you have to make sure that you have an interaction between the systemic component, I mean the global circulation, and the local component, and the local features. I mean, we have a feedback mechanism that you have to account for. And this is a very pictorial representation of what you did. We call it geometric multiscale. We are actually using an interplay between the local 3D and global 1D and global 0D. Now we see it again. We have green capillaries where we use zero-dimensional models or in differential equations. You have the big carotid artery, say, which we use three-dimensional models as before. And then we have for the rest of the circulation the most important components of arteries and veins, order of 100, say, which we use one-dimensional models. So we use 3D for the carotid artery or for the ascending aorta or for the iliac or the ventricle, say, and then use 1D everywhere else, unless at the peripheral circulation in which is not even the 1D would be affordable, and there we use the electrical circuit analogy. So here is the paradigm. We use the monster problem that we have seen before, pre-linear Stokes, coupled with the 3D elastodynamics for, say, bifurcation of the carotid artery, just to make an example. Then we use a one-dimensional Euler equation. You see that these would be one-dimensional equations for the most important vessels and arteries. And then we use for the peripheral resistances, we use the analogy with the electrical circuits, and this boils down to the use of systems of order differential equations. So we alternate 3D, 1D, and 0. So this is the equation that we have seen before. so there's no need to elaborate. And we make assumptions. For instance, we made the assumption that UZ, the longitudinal velocity, is higher than the other components of the velocity. Then we assume that UZ has a prescribed steady profile. Then we average over the sections, and we impose the static equilibrium of the vessel, and we obtain a one-dimensional problem, which is this one. So this is a much simpler problem. It's an Euler system of equations like the one that you have in gas dynamics, completely different type of description. And now Q is the flow rate, A is the area of the vessel, the section area of the vessel, which is unknown. Right? We are describing the problem as being a one-dimensional problem, but we know that this is not true. It's a three-dimensional problem, and the way to recover three-dimensionality is through the area of the vessel. So we have pure hyperbolic system instead of the elastodynamic problem coupled with the Navier-Stokes equations. And if you go further, then we have to linearize the equation. For every single piece, we take an average also over the longitudinal section and replace the space variability by a single value, the average, so we only have time variability. For every section, for every artery, we just use average flow rate and average pressure, for instance. And by so doing, we end up with a simple system of ordinary differential equations. And this is like using electrical circuits. And of course, there is a different meaning of the variables, right? In electrical circuits, we have the voltage, here we have the pressure, the current is replaced by the flow rate, the resistance by the blood viscosity, the inductance by the blood inertia, which is due to the convective nonlinear term, and the capacitance by the compliance of the wall, by the deformability of the wall. So this is the way we couple the 3D with the 1D visibility. And you call it geometric multiscales. Now, there are many mathematical problems. Some of them are really tough and challenging. And the first one is that this 1D was proposed by Euler himself long ago in 1775 in Basel. Euler at the time was professor of anatomy in Basel, and he celebrated Euler equations were not proposed for gas dynamics, but for blood flow. So Euler was really looking for using blood flow description in a cylindrical vessel, straight vessel like this one. So his equations were proposed for this specific context. And now we want to use it for a network of vessels. So how do we account for curvature? How do we account for bifurcations, for instance? Well, at bifurcation, we enforce the continuity of the total pressure and the conservation of mass. So we make a patchwork of these different pieces, and we use these equations and the interface. Besides, we have to modify the equations, but we don't talk about that. We have to modify those equations by accounting for the curvature. And by also accounting for what is called the tapering. Our vessels do not have the same diameter. We start with the aorta, which is 1.5 or 2, depending on the subject, and then we go down to the level of the small vessels, and every single tract is characterized by the tapering, I mean by a changing diameter, right? So you can insert these modifications in the Euler equations, and ending up with a system of Euler equations that is suitable to describe, you see, the most important component of the whole circulation, the most important arteries and veins, and all of them are well calibrated. They're well described by physical parameters. So this is an example of the way it shows, the solution shows. These are 104 vessels, and here is the wave that propagates through the vessels. So the size indicates the value of the section area as far as the pressure wave propagates through the vessels. So this is the same computation, however, At the peripheries, we introduce the electrical circuit to account for the local resistances. So this is a couple 1D with 0D at the very end. And it's important that you insert also the 0D because otherwise the solution will be quite different, and this is more realistic than writing absorbing boundary conditions. So this is a fully one-dimensional model coupled with zero-dimensional model at the peripheries. And this is where we are. We have described by one-dimensional models a complex system, but now we allow to couple it with three-dimensional models because maybe you want to use the same simulation as before for the aortic arc, which were 3D. So how do we couple the 1D with the 3D now? And this is what is called the sequential multiscale. So here is the idea. We have an artery which is actually a 3D, and we oversimplify it by considering one piece of this artery described by 1D. And this is the way the grid shows up in the 3D case, and then in the 1D case we have one-dimensional grid. Now here is a real case. This is the abdominal aorta with different branches. This is the thoracic aorta. This is the celiac artery. This is the left renal artery. This is the abdominal aorta. This is the right renal, and this is the right renal, and this is the superior mesenteric. So, and all these branches are now replaced by one-dimensional pieces. So, a couple 3D and 1D, and what you see in the different pictures, there are the wavelengths that characterize the flow rate, right? Which is different, actually, the different components. And this is a very simple simulation with a 3D with 1D, with a 3D with a 1D continuation. And I'd like to emphasize the fact that the 1D continuation is important at the modeling level, but is also important mathematically because if you only have a 3D and you cut this 3D, you have to invent boundary conditions here. This is very difficult for a deforming vessel. So in this case, when you have a 1D, not only you can describe your problem at large, but you can also have a correct way to allow your waves to leave your domain safely. All right, this is the global picture. We want to use 1D everywhere with zero dimension in the peripheral vessels, and with 3D in a specific environment where we want to have a much better description. And this is just a detail of the solution. You have this 3D, and the rest is 1D, and here is the way the 3D and the 1D communicate each other. We call this sequential multiscale because we have 3D followed by 1D, or 1D followed by 3D. But saying this morning that you can also regard it as being, you can also use the same kind of idea to consider an embedded multiscale in which the 1D is embedded into the 3D, like in this case, this is the brain, this is the, what is called the circle of Willis, or the polygon of Willis, and which is described by a network of one-dimensional pieces. And in this case, we want to simulate the oxygen transport in the brain. So we have to couple 1D and 3D. And we have to couple two different models. One is the fluid model. The 1D in the artery is described by the Euler equation that we've seen before. And the 3D in the external domain is described by porous media, the Darcy equation, Darcy-Brinkmann equation. At the same time, we have diffusion and convection of oxygen in the 1D, which should be coupled with diffusion and convection of oxygen in the 3D. So we need it's the same simulation, but now we're saying the pressure, pulse time pressure. So we need to, you see, to use the one-dimensional model for fluid. These are the Euler equation that we've seen before in this one-dimensional vessel, coupled with a two-dimensional Darcy-Brinkmann equation for the pressure in the tissue. Tissue is external tissue. So you have to combine these two things, and how do you communicate one another? Well, through these flux carriers, which is phi, which depends on the pressure of the tissue and the vessel, multiplied by the delta Dirac function, which is supported by this lambda one-dimensional line, and the same here. So you have these terms that are there to allow the communication, and here is the same type of. Let me see if I have to. Then we have the same kind of interplay for the transport of oxygen or of any other drug, say, or nutrient. You have convection diffusion equation in the external tissue and convection diffusion equation in one dimension, which is the Arctic, say. And again, you have this theta, and in this case, these are the concentration of the oxygen in the tissue and in the vessel, and theta is, for instance, U in the vessel minus the average of U in the tissue. The average is taken on an external circle. So you need to insert into the equation some exchange mechanism to make sure that 1D and 3D communicate correctly. So these are very complicated models because you are really playing with different geometrical dimensions, and not even the analysts have an answer to this problem. We look for analysis, mathematical analysis, look for solutions of this type of equations. It's not in the literature, so you have to develop your own investigation method. That's a different application in which you see that you have control and optimization. It's a reticular access device. In case the ventricle does not pump with the right rate, then you have to assist it with external pumps. And here, of course, there's a lot that Marek can tell us and teach us about the way these pumps work. And here we just simulated the interaction between this external vessel with the aorta, and so we simulated the. You see this this VAD, which is artificial, and the ascending aorta. These are detail of the solid model and the simulation, and this is the way the blood is pumped. And of course, you have recirculation here, you have backflow. Luckily, because coronaries are departing from there, so you have to feed the coronaries arteries. And our analysis here was focused on two issues. One was the optimal shape of this external vessel, and related boundary conditions. How do you pump? What is the optimal quote-unquote pumping rate in order to make sure that you have what you are expecting to have in terms of flow redistribution. So these are optimal control and shape optimization. And the second one, so this is just detail the solution. And the second one was how to couple this local analysis with the global analysis through one-dimensional models and zero-dimensional models. So we described the pump and the external environment through zero-dimensional models, in which we use the analogy of electrical circuits, and we couple it with the three-dimensional model here. But of course, we could replace the circuit that described the pump by a real three-dimensional pump if we had this type of simulator. In that case, again, you would have this 3D interplaying with the 1D and the 0D. So here is our system. Again, it's a geometric multi-scale. You see this external stuff, external vessel, and we couple it with one-dimensional, external one-dimensional, and eventually zero-dimensional for the pumping. So it's still in 1D coupled with the 3D. And on top of that, you have this optimal control and shape optimization for the specific vessel. I'd like to use this maybe 15 minutes before making another break to say that so far we have seen the way the circulation takes place, but of course the main engine is the heart, and you have to incorporate in this model the heart, and the heart is a very complicated object to model, as everybody knows. And here, I'm sorry, the thunder is in Italian. Okay. The coordinate square means the heart of the golden crown. Okay. Well, it's just. So I guess for those who are completely, unaware of the problem, it's I may remind you some basic anatomical and physiological information. You have the venous blood is injected through the right atrium and comes from the vena cava, superior and inferior. Then you have this valve, which is a tricuspid valve. The blood goes into the right ventricle, and through the pulmonary valve it's sent to the lungs for the oxygenation. It gets back through the pulmonary veins, enters the left atrium and through the mitral valve into the left ventricle, and then it's pumped outside to the aorta through the aortic valve. Okay, that's the basic mechanism. And the cardiac muscle consists of cardiomyocyte cells, which are aligned along fiber directions and collagen sheets. Fiber and sheets. Then you have the calcium ions. It's the positively charged bivalent calcium. And the intracellular calcium concentration is the one that triggers the sliding of thin and thick filaments inside the sarcomeres. And this is the most fundamental and basic mechanical process from which the whole contraction mechanism takes place. So it's a spatially multi-scale problem. You have the whole body, which we solve our fluid dynamics. Then you go to the organ level, which is the order of a few centimeters. Then you go to the structure of the tissue, and the cells are order of 0.1 millimeters, and then you have the sarcomeres, which are the contractile units inside the cells, which are 0.002 millimeters. These are characteristic length, or dimension. And besides, you have an intrinsic temporary multiscale in nature, because see the waves of calcium, polarized calcium, propagate as the order of 10 to the power minus 3 seconds. These are characteristic time speed. And the polarization and depolarization waves is every 10th of second. The cardiac cycle is every second, and then the response to the metabolic system is order of 10 to the power hours. And of course, the lifespan is hopefully much higher. Well, these are some of the challenges. You want to have a correct representation of the external tissue. You want to go from cellular forces to tissue stresses, because you want to allow for your model to be able to represent the deformation. You have the electrical signal that propagates very quickly. You have this propagation that affect the local deformation, and then you may have some macroscopic modeling issues like those where you have, for instance, pathological behavior of valves or the pumping mechanisms. So the electrophysiology is one that dictates the cardiac cycle. Muscle contracts driven by the CO2 processes. The mechanism of activation dictates the contraction of the heart. Contraction determines the pumping or the injection of blood into the ascending aorta. And ideally one should account for all these processes if one wants to accommodate all the possible behavior. So these are very preliminary simulations. For the electromechanics, we try to couple the electrophysiology with mechanical deformations, but these are just pictures. How good they are, well, this is not the issue. They are certainly very bad in the sense that they are not neither verified nor validated, just proof of concept showing that you can calibrate different parameters and using them. And this is the modeling. This is the modeling representation. So you need PDEs for the electrophysiology. You have an exchange of potential and aortic current, and you need ODEs for the aortic activity. Then you want to describe the cardiac electrofluid structure coupling. You have the activation that generates an active strain that allows the muscle to deform. So you need PDEs for the nonlinear elasticity. And then once you have the deformation, then you have a fluid structure problem because you have the ventricle that deform and the blood is inside, and then the fluid and structure as the one that you had in the vessels. However, in this case, the fluid is much less stable, or if you want, more unstable. It's not really turbulent, but there's still a debate on that. But perhaps it's not turbulent, but it's very unstable. So the dynamics is completely different. I will not elaborate on that, but you might have heard about these names. These are the system of so-called bi-domain equations for the electrophysiology. V is the electric potential, Vi the intracellular and extracellular potential, W are the ionic quantities. And here you see you have diffusion, advection, it's diffusion and reaction equations. So these are, roughly speaking, parabolic equations, nonlinear parabolic equations. Actually, it's a system of nonlinearly coupled parabolic equations. And they are coupled with a system of ordinary differential equations. So this should be regarded as a straight VT. And this is to express the ionic model. So these are the electrophysiology equations. Then you have the activation, and you have the generation of the active strain, and then you need a PDE for the nonlinear elastic equation. This is a possible nonlinear elastic model for the deformation of the muscle. And then you have, of course, the coupling with the Navier-Stokes equations that can be written again in any form or in other representation, depending upon the choice. It's a very heterogeneous model with different time and space scales. Just to give you an idea of the basic figures, near the propagating front of the excitation, delta t should be of the order of 0.1 millisecond, which means 10 to the power minus 4 seconds. And h, which is the space size, it should be of the order of 10 to the power minus 2 millimeters. For the muscular contraction, then you may need a much coarser space and time discretization. Delta t could be of the order of 100 milliseconds, so 1/10 of a second, and h is 10 millimeters, so much higher. Now for the blood flow, delta t is order of, I'm talking about characteristic sizes, right? 1 millisecond, and h order of 1/10 of millimeter. So, I mean, how can you accommodate with all this delta t and delta x, while the three phenomena are strongly coupled together? I mean, the co-presence, coexistence of all these phenomena. Well, how do you couple? You can use monolithic. In that case, you have to opt for the most severe delta t. Or you can you can use, you see a segregated approach in which the electrophysiology, the one that is more demanding, is separated from the fluid structure interaction, muscular and ejection fluid. This is a typical approach that some people try to follow, but there is not that much so far in this respect. In fact, there is another possible point of view, which is somehow alternative to this one, or complementary, or nobody knows. Electrophysiology drives the phenomenon during the systolic peak, fluid mechanics drive the phenomenon during the diastolic peak. That's another way to split the problem. So we infer the systolic peak and then the diastolic. So in the systolic peak, it's critically important to solve the electrophysiology correctly. In the diastolic peak, it's extremely important to solve the fluid structure interaction correctly. So these are just really attempt at the solution. Again, it's not that important, but just to show that you can somehow calibrate the model. And this is yet another application in which you are trying to face some specific problems. You know, when you need money for research, you use, okay, this is not really an official statement, that it's a kind of rule of thumb. You tend to use, say, I tend to use money for, say, public money for describing the physiological model, and then using external money to solve specific problems that are raised by external counterpart. And the external counterpart is a medical doctor, very often it comes with, they come with pathological problems. Right? For instance, this one. Now you have the tricuspid valve, the one that is responsible for the ejection mechanism. This is the physiological situation, and this is the case that you have I'm sorry, this is sorry. So this is bicuspid valve, right? Instead of this, you have this. And you see, it's not negligible. I mean, 1 to 2% of the population have this bicuspid instead of tricuspid, and of course you can leave this bicuspid. Very often it's not even detected. Right? And in the 60% of the patients with bicuspid valve, there is, however, the possible formation of an aneurysm because of different type of flow pattern. Now, the scope, the aim of this model is to try to simulate the situation in both cases, and you see, this is bicuspid, and this is tricuspid. I mean, the flow feature is very different. I mean, velocities are different, flow distribution is different. This is bicuspid, and this is tricuspid. Much more regular here than there. And, so try to better understand what is, for instance, the friction or the shear stress, which is due to the on the wall, which is due to the bicuspid, and this one that will eventually determine the formation of aneurysms. And of course, an used problem is how to assess the risk for the aneurysm to break over the years, over the time. So that's why fluid dynamics can be important at this level. And of course, fluid structure interaction is very important in this case. And this is just a simulation in which you see that you have indeed bicuspid instead of tricuspid, and you see the way the flow is actually impinging and affecting the wall where the aneurysmatic sac is going to develop. All right. I will stop in 2 minutes, but still on the heart side. This is a malfunctioning of the electrical activity of the heart. This is the 2 ventricles are not pumping, say, in a synchronous way. That's why they have to make a pacemaker or activate an external impulse in order to realign the pattern. And so that's why solving the Balaban equation accurately is important, and solving it also on the presence of this external mechanism triggering mechanism is also important. These are pathological cases in which you have a very nice from the mathematical viewpoint, but nasty from the practical viewpoint, wave pattern, which are due to arrhythmias or tachycardia. And of course, to study the way you can either scare the tissue or using external impulses to resynchronize the heart mechanism, say. And that's the very last picture that we show for the heart. This is, as far as I know, the first attempt to reconstruct the Purkinje fibers that are very difficult to detect from the clinical level, which are responsible of the fine propagation of electrical signals. And the very first time for a patient-specific, for a specific patient, say, and these are again extremely important to see, to construct the map of activation of a given patient through the Purkinje fibers in order to, especially on patients affected by pathological electrophysiological behavior, to see the way this can be cured, for instance, by scarring appropriately some specific part in order to restore, to break this, say, sustained electrical signal, and to restore synchronized behavior. All right, I think we stop here, and I will perhaps devote the last part of my talk to model reduction through reduced basis and reduce parameterization of the surface in cases in which the surface is very important. All right. So the last part of this presentation will concern the use of reduced models, reduced order models for problems with which depends on parameters, and it's a kind of mix-up of ideas. So it's not, it's not very linear, but I mean, just giving you some hints on some different aspects that we're working on. So now the last part of the picture here, and we can generically address this part as reduced basis methods, more or less, as you shall see. So what is a reduced basis method, first of all? Well, a reduced basis method is a method that try to solve partial differential equations depending on parameters. Now, parameters can be physical parameters, for instance, to describe material properties. They could be boundary data, they could be initial data, they could be source terms in the equation, or they can be associated with the geometry of the problem. So describe an object through parameters, and then we enter, as we see in the PDE problem. I was saying this morning that another typical example is when you have many query and real-time simulation, in which on a problem depending on parameters, you want to produce fast answer by improving the offline-online paradigm or stratagem. So you want to work most of your time offline and only for a very tiny part online of your time online. This is a picture that I borrowed from a presentation by Professor Quateroni from MIT. It's slightly elaborated, but the essence is the same, and it describes the idea, the basic idea. So assume that you have a partial differential equation that depend on parameters, say mu. And assume that you want to make a simulation for many different values of the parameter. For instance, you want to solve the fluid equation in this bottle, and I want to describe the surface by parameters, and then I want to solve my problem for different type of surfaces, and therefore for different type of parameters. So for every choice of the set of parameters, I have to solve the equation. So the classical finite element analysis, for instance, would consist on solving the same equation with different parameters, and this is the amount of time that you have to devote to your computation. So every time, the same time, basically, same amount of time, because you're solving the same kind of problem with different values of the parameter. With the reduced case approach, we want to defer most of the computation offline, and then solving online for every new value of the parameter in much quicker, say much quicker your problem. So most of the problem will be done offline, and this is the parameter independent, while all the problem which is parameter dependent should be carried out online. So it's essential that you separate the parameter dependence from the parameter independence. What is parameter independent, you do it offline, or what is parameter dependent, you do online. That's it. So, mathematically speaking, you can envisage having a situation like this one. See, assume that you have this, this is a flow, a simple flow in a channel. And may change the Arrhenius number of the flow, you may change the geometry of the vessel of the channel. Right? Here there are two different channels. This is characterized by mu1 and this is characterized by mu2, say. And mu1 is the set of parameters to describe this channel here. But maybe it's this length, this length, this length. All right. And assume that instead of two channels, you have many channels, right? So if you look at the solution of this flow problem, this solution is described a manifold, this line here. See, this is the set of solution. It's a manifold. I mean, for every value of the parameter, it changes continuously. You have a solution in the phase space, in the space of the solutions. These are kind of ideal solid space in which your solution, to which your solution belongs. So, how can you solve this problem? Instead of using, for every new value parameter, the full strength of finite element. Well, you can select a certain number of representative parameters beforehand, say mu1, mu2, mun, straight n, computing offline the solution corresponding to those parameters, and using these as basis functions instead of the classical finite element basis functions. Classical finite element basis functions are generic functions. Those depend on the problem. So you generate those basis functions, and then you look for a solution which is a combination of these solutions here. So assume that capital N is order of 10. Then you have 10 basis functions, and then if you have a new parameter, you look for the new solution as being a combination of these basis functions. So the problem has dimension straight n. Straight n is order of 10. So you solve a finite element problem whose dimension is order of 10. Instead of solving a finite element problem whose dimension is order of curly n, and curly n is the number of grid points, order of millions, of 10 millions, of 100 millions. I mean, in the Alfio case, it was order of 300 millions. Of course, you can change the problem and change the dimension. All right. So you compute offline the solutions corresponding to these parameters. This is a big effort because you compute, say, 10 times a problem whose dimension is 1 million. And then online you compute a problem whose dimension is 10. 10 by 10 matrix. That's the idea. Of course, you like this red curve, which is the curve interpolating the pre-computed values, could approximate the black curve for any value of mu. And this is hard mathematics. And actually there are beautiful papers by Wolf van Damen and Ron de Voor and Albert Cohen showing that in some specific cases you can prove that the red curve tends to the black curve exponentially fast, depending upon capital N. So, parameters. They can describe physical coefficients, they can describe sources or boundary conditions, they can describe geometric configurations. And here, you have different types of descriptions. You have direct, clear meaning of those parameters. For instance, in this case, they can represent the size of this bypass vessel, the size of this hosting coronary artery, the size of this angle, the length of this coronary artery. This is a simplified coronary artery, say, with a bypass. They may have a more abstract meaning. For instance, they can represent the displacement of selected points in case you use, for instance, free shape parameterization or radial basis functions. So this is not that important. The important point is that those parameters are there to represent the geometry of your domain. Right? And they enter into the equation. What should you produce at the end? Either the complete solution or most often something which has a specific engineering interest, which is called output. And this could be the energy, the vorticity, the drag, or the lift, or an airfoil, and so on and so forth. And these could be distributed quantities or selected quantities, like stresses at some point, pressure drops, etc., etc. So the output is not necessarily represented by the whole solution, it might be represented by specific components of the whole solution. If the parameters represent physical coefficients or sources or boundary conditions, most often you resort to an optimal control problem. If they represent the geometric configuration, then you have a shape optimization. And we typically try to use reduced basis methods and shape parameterization to produce a shape optimization for multiple shape exploration and hopefully to have real-time simulation. We are not yet there. In some cases we are almost real-time, but in more complex cases we are very far from being real-time. But I think this is more or less the roadmap, the direction of propagation. Alright, this is just a kind of meta-algorithm in which you see the way the different ingredients in the reduced basis algorithm play together. You have the shape parameterization, you have finite element basic structures, which are the basic stiffness or right-hand side components, which are independent of the parameters, so all this is offline. You have the selection of the basis functions, which is based on a greedy algorithm, and you have the development of posteriori error estimator. All this is offline. That's very expensive, very heavy, it's offline. While online, you have specific parameters, and then you need to compute those components of the solution that are parameter dependent and that cannot be computed offline. And typically, you resort to solving a very reduced problem. The dimension of this is straight n. The dimension of this is curly n. So this is order of millions, this is order of few tens. So that's the way you can have the two things interacting with one another. All right. I would like to make a few comments, and I hope they are not too elementary, on because I'm not sure I'm really aware of what you are doing in your group. I'm sure some of them will be very elementary. How to represent shapes using parameterization, and this is an example. This is a basic domain, and this is a milk bottle, say, and these are possible deformation of this milk bottle. And of course, this is described by parameters, mu1, mu2, mu3, mu4. I mean, specific values of the parameter. You have a reference domain, with fixed computational mesh. We define a parametric family of diffeomorphism, I mean invertible maps. T goes from Rd times P into Rd. P is the set of parameters describing the object, and you want these maps to be regular enough. Then you have a family of admissible shapes, theta AD, AD stands for admissible. These are the shapes of omega 0. Actually, this 0 means original domain, the actual domain. So you have omega 0, omega O of mu is the transformation of the reference domain through the map. So omega here is the reference domain, omega O is the original domain, which means it's one of those guys here. It's the real physical domain. And then you want to transform back your PDE, which is set up here or here or there or there, back to the reference domain by change of coordinates. So you go from the original domain that depends on mu, for instance of the gradient time gradient if you are solving the Laplace equation, back to the reference domain. And here is where you see this T map enters. How do you construct this map? Well, you can do it in an elegant manner or in a less elegant manner, more constructive one. One possibility is that you take your domain, you divide it into subpieces, and every subpiece you transform it parametrically and affinally to the reference domain, like here. So you have every piece. You see, this is the original domain, and this is the reference domain, and the original domain is represented in terms of parameters that you see here, this diameter, this length, this angle, etc., etc. And this is the reference domain. So you see the map is piecewise map for every subdomain, and it depends on the actual coordinates through affine transformations. And of course you have global continuity conditions. You want to make sure that the maps, different match correctly through the interface of subdomains. And here is the type of complexity you can afford. Say you have a domain which is external to the airfoil, you split it into subpieces, subdomains, and then you map every subdomain through this map. And every map is characterized by few parameters. Another alternative is to use what is called free-form deformation. Here the process is quite different. You have the computational domain, which is the external domain to an airfoil, just to make an example. This is the actual domain, the original domain, it depends on a set of parameters, and this is the reference domain. So what you do, the reference domain is called in this case D, is the domain external to omega. Well, you transform this D into a D hat, which is a square. You don't see the airfoil any longer, and this is made on purpose. This is a very simple map. You are transforming the rectangular domain into a square. In 3D, of course, it will be a parametric domain into a cubic domain. Then here you use point that you call control point, free-form deformation control point. Then you introduce a map that deforms this point. And when you deform this point, you combine with the psi minus 1 map, you retrieve the original domain with the deformation of your omega, say. So the parametric map is a linear combination of coefficients, say you have coefficients here depending on x type Bergstein polynomials. And these depends on the parameters that you have So basically, when you change the parameters, you change the position of the nodes, and therefore you change through this map, you change the configuration of your original domain. We use these parameters and these control points to actually change and transform any figures, any geometry that you may have at the very beginning. Note that this is not an interpolatory procedure, so you're not following, for instance, the deformation of the boundary. I mean, you recover a deformation of the boundary, but you don't have any precise direct control on any point on the boundary of your domain. These are simple examples in which you can recover solving the Navier-Stokes equations and starting from initial shape and actually recovering an optimal shape by using 9 moving control points, and only 6 of them are actually movable, the other are fixed. So with very few points, very few control points, you can actually drive your system to an optimal shape. And since these control points are the parameters in our reduced order model, then at every step we have to solve a problem which has this size, order of, say, 6 by 6. So it's a very simple problem in the sense that you solve Navier-Stokes equation at every step with only 6 degrees of freedom. An alternative is to use the radial basis functions. Now you can better follow the what's happening on the interface or on the real geometry, say, and well, radial basis functions are functions that depends on distance functions from selected points, and there are several ways to set up radial basis functions. You don't see them, they're here. One is Gaussian, the other is multi-quadratic, the other one is cubic, etc. etc. So use a generic function to describe a distance between 2 points, and you may want to use these radial basis functions in order to deform your domain. And I'm not at all expert on those kind of things, but I had a master's student who is from aerospace engineering wanted to show that these are very good tools to manipulate and to work on eigenfunctions of a complicated structure. And this was just to show that you can go from initial configuration to a final configuration by reacting on very few points. And this is order of 10 control points. These are the red buttons. So you can play with this, and of course making a lot of computation offline, computing the eigenmodes, and then using few of them, and then online to solve 10 by 10 problems in order to deform complicated structures. And we use it for arteries. These are 2-dimensional bifurcations of an artery, and in this case you have 12 control points, which are the red bullets, and we control the deformation of these points. Then through RBF we can go from this background blue artery to this new green artery by solving, in this case, an optimal control point again. A third option is a bit more involved and perhaps a bit more mathematically tricky. It's using transfinite interpolation-based maps. This is an approach that was proposed, I guess, well, originally in the framework of spectral methods by in the 90s by many people, but in the framework of reduced basis methods by Madé and Ronquist, and we generalized it. You see, you have to solve local Laplace equations on different faces with different kind of boundary conditions. It could be Dirichlet or Neumann boundary conditions, and by so doing, you can, you see, reproduce many different shapes by linear combination of very low number of basic components, and therefore again reducing your space dimension to a very reducing your problem, to a space dimension, to a subspace whose dimension is very small. Here is just an attempt to compare the pros and cons of the different approaches. And again, please don't take this as real truth, but as a kind of qualitative assessment. We've seen 4 different ways: the piecewise affine transformation using domain decomposition, the free-form deformation using Western polynomials, the free-form deformation using graded basis functions, and the transfer interpolation. The pros is that in this case, this is automatically affine, and you can, so RDMeet is a reduced basis library that is written in matter, that is available on the web, so you want to use it, you can use it to solve problems with reduced basis, and this is done automatically in this library. The cause is that it depends on the mesh, and the regularity is only CZ. The patching is only CZ. The free-form deformation of Western polynomials is independent of the mesh, is very efficient to implement. However, it requires degree to be tensor product. It is not interpolatory, and this might be a problem with when you want to have a better control on the interfaces. And free-form deformation with graded basis functions, mesh independent. You can scatter control points where you want, and it is interpolator. Now, what is left to the user is the choice of the size of the support, and it might be quite expensive because of the very nature of the graded basis functions. When you use transfer interpolation, it's based on edges, so it's very simple. Once you know how to describe geometry of the edges in your structure, you can do it. However, the cause is that you require the solution of partial differential equations, which are not that difficult because they're based on the Laplacian, but still are relatively difficult, and they can only treat simple geometries, those that can be represented as the union of faces connected through edges. Here are some examples of applications in problems that are either very simple or less simple. These simple problems, a two-dimensional problem, we see is a bypass, it's a coronary bypass. This is the hosting coronary, and this is the bypass. And I'd like to optimize the shape of the bypass in order to produce an output which is the best possible. What is the output? Well, typically, when you create a bypass, you are creating a recirculation downstream. And this recirculation may create vorticity and high shear stresses, and high shear stresses can create plaque accumulation. So you put a bypass in order to remove say, if you put a bypass, it's because you have a coronary artery that is occluded here, but over the months you are creating an occlusion down there. So is there an optimal shape of the bypass? So this is a two-dimensional analysis. Here is geometry, the original geometry, and these are the control points. We want to operate on those control points. We want to use all these control points to create our free-form deformation map, the one based on Bernstein polynomials. But in fact, only the red ones will be active. So we have 4, 6, 7 control points that are active. Actually 8, I missed one somewhere, I don't know where I put them. There are 8 control points that are active. So this means that you have to solve at every iterative step, you have to solve an online an 8x8 problem for Navier-Stokes. Right? And you get a vorticity reduction on the order of 40% with respect to the original shape. So this is the original shape, that's the final shape that you obtain by acting only on those control points, and that's quite remarkable. So this is yet another application. This is a femoral bypass graft, and in that case you can get a reduction of 50%. Now you are acting on 6 parameters, and now this time we're using reduced basis. I'm sorry, we're using graded basis functions. So RB stands here for graded basis, even though we are using it in the framework of the RB, which is reduced basis. We use RDF to describe arteries of different patients by the help of very few parameters. And that's very important if you want to construct, for instance, an atlas of fluid dynamics for many different kinds of patients. So instead of solving for every single patient, for every single geometry, a new problem with, say, millions of variables, you parameterize all these arteries by a few parameters, and then you make computations offline, and then online, big computations offline, and then online, you compute only the problem with a very reduced size. We'd like to go to real-time simulations. Of course, you're very far from the real-time simulation, but it's only two-dimensional problem. But you see, this is a whole. I mean, this is on a PC, and you can solve Navier-Stokes equations on a new geometry from a new patient by using the library that you computed before in very little time. So we use it for various applications, and one is shape optimization, and you go, I think this you already seen actually, and well, this picture, but you basically already seen. What I would like to tell you that very often, however, these simplified representation are also used in the medical literature. So doctors behave with following protocols. And the protocols do not foresee the solution of PDEs, of course, right? But they're based on some kind of quote elementary information or basic information. And one of those information is how thick is the plaque, what is the percentage of the plaque, what is the angle of the bypass, how big should be the bypass artery with respect to the size of the hosting coronary, and so on and so forth. So you find these pictures you see in medical journals, and you see these parameters that identify the type of intervention. So that's why it's not completely unrealistic to use this parametric representation of complex structures for medical purposes. The purpose here is not to obtain solutions that are accurate up to 1%, 2%, 2 per thousand. This is good in engineering practice because problem is much better understood, but not necessarily here. Here the interest is to produce something which has a better trend. You want to, for instance, tell the doctor that this behavior is much better than this other behavior, or that this size is better than this other size, etc., etc. So this is just a proof of concept. We are solving the previous problem with reduced basis functions. It's a very simple computation. Now we're solving the Stokes equation, not even the Navier-Stokes. We use a finite element where 36,000 finite element nodes, so the problem is relatively simple, but not too simple to be carried out real time. And we use a lattice of free-form deformation contour point, which is 5 by 6, but the actual points that are used are 8. And so we use 30 points to describe the map, but only 8 of them can actually move, can actually change. We use 20 basis functions. So our online problem has a dimension which is 20 by 20, and we have 222 components, affine components. We split our problem into 222 components, and this is the typical size of the reduction in terms of complexity. We go from the dimension of the linear system is reduced by a factor of 500, and the time is reduced by a factor of 100. So here is 2 orders of magnitude of saving, which are due to this offline-online split. Here are the pictures that relate the actual shape before and after the bypass. And this is Navier-Stokes this time, and you do the same basically. This time you use very few points. You see only 4 parameters. which describe the possible shape of the obstructed artery, and you can of course create afterwards a scenario of different possible solutions. You see the way you have energy dissipation depending upon the values of the two parameters. You can easily find out picture of this type that drive the doctor in understanding where you should move in order to obtain a specific kind of indication. In this case, the indication is the energy dissipation. The higher the energy dissipation, the higher the shear stress on the external surface and the most critical flow field. All right, I think this is more or less what I wanted to tell you. There is time if you wish for questions, discussion.
So, questions or comments? You think I will ask one question? So in 3D there are of course these many different ways of parameterizing the surfaces. Have you settled now for 3D arterial simulations on one way to deform them, or?
We tend to use, this is the state of art of our knowledge now. Today, if I should say what we are actually using, we eventually end up by concluding that for say for the cells, when there is very small deformations of cells, which are not the case here, right? We definitely prefer greater basis functions with an inverse distance rate. And it's the best way among those that we have tried to handle with the mesh motion and with the transformation of information between completely different grids. So where you have very big deformation of the very big mesh motion and large deformation, brighter basis functions seems to be, in our experience, seems to be the best way.
But that's the one that is most expensive probably. So
yes.
if you have very fine mesh resolution, you have many distance computations between the control points and the...
It's true. We are improving on that, and indeed the very last result that we had shows that there is a lot of room for improvement in terms of computational complexity. But you, it's the way that you prefer when you have very big mesh motion to prevent the formation of invalid grid or grid with very low quality. Invalid grid is when you have, say, negative volumes, and bad grids is where you have very stretched grid, which are not wanted, say. For arteries, we tend to use free-form deformation. We do not, in this case, have to deliver accurate results. We're far from being able to deliver accurate results because the model is so affected by so many uncertainties in terms of original geometry that you get from MRI, in terms of radiological parameters, in terms of boundary conditions, initial conditions, and so on and so forth. So we really need to deliver results which are credible, plausible, not necessarily accurate, and the free-form deformation seems to be very, handy and efficient and quick way to proceed. So we are using these two different approaches so far, but it's last from being the final work. We're really exploring and while when you use the reduced element basis method, which is the reduced basis method not on a single domain but on multi-domain, then we tend to use the reduced basis method on every subdomain offline, and then you have to patch the whole thing together. There we use a transcript interpolation. and which is very expensive, but it allows us to guarantee the right exchange of information, for instance, the continuity of normal stresses for the fluid. Otherwise, you generate a solution that's not consistent. So we are far from having a unified opinion. It really depends on the problem.
Questions, yeah, please.
Just a curiosity. You said before that you want to take into account also uncertainty in the future, in the near future. And how can you deal with this type of concept with reduced basis? Is it possible in the framework of reduced basis, or you need something more?
Yeah, I have a student who is now Champagne in Lausanne, who is exactly working on this aspect and combining reduced basis with uncertainty quantifications. And so far, he has basically had, not sure, I think I don't have the results here, but yeah, try to, for instance, simulate the whole arterial tree that are shown before with one dimension, and using the parameters that characterize some of the major components of the arterial tree in terms of length or thickness, of density of blood, etc., and using those parameters affected by uncertainty. So you solve the one-dimensional system everywhere with uncertain parameters. And you want to see basically the output is which are the most sensitive elements that affect the solution specific points. If you're interested, I can send you a couple of papers which are just preliminary reports, and if you send me a mail, I'd be happy to send you this things. Yeah. But the problem is there is really the one of combining the reduced basis with the uncertainty quantification of some specific parameters.
I'm just wondering how well the solution is represented by this being used all other places. I could guess that, well, if the geometry displacement is very small, then the nodes are representing the solution quite well. But if you have a lot of changes in the geometry, or maybe vortices that are establishing due to the changing geometries or something like that, is it really so well represented?
I would probably say that this is not the crucial factor. If you, I mean, the deformation in terms of, if you look at the accuracy, there are several ways to represent the deformation of the geometry. Some are interpolatory, like those based on either direct representation of or the real basis functions. Other are not. So if you're really interested in catching the sharp deformation, it's better to use interpolatory approaches. And then the reduced basis can do quite well, because reduced basis method is, say, a method that is potentially capable of producing a solution that converges to the what is called the truth solution, which is the finite element solution. Assuming that you don't know the exact solution, right? As soon as you have a problem, and then the best of your possibilities, you can solve this problem by finite elements using what, I mean, the amount of degrees of freedom that you estimate necessary. This is called the truth solution. Then, as an alternative, you can solve it by the reduced basis method, in which you pre-compute a certain number of representative solutions, say capital N, and then you look for a new solution, which is a linear combination of those, and solve the same type of problem, say the Navier-Stokes equation. Now, this reduced basis solution converges to the exact solution, which is the finite element solution, say, with a rate that in some cases can be shown to be exponential. So, order of exponent of minus n, right? The theoretical proof is available only for some very specific linear problems, like the Laplace equation. But you have an evidence, a numerical evidence, this is actually the case also for many other problems. Now, what does that mean, to go back to your question? If capital N is too small, then you are using very few parameters to describe your deformation. If these few parameters are very far from being able to capture the essential features in our deformation, your solution will be poor. But if you increase the number of n, then you are rewarded by the fact that you have a convergence which is of exponential type. So you should use a number of n which is good enough to represent the expected worst possible scenario in terms of change of the solution. In those cases that you have seen, like the, carotid artery, the shape is not that regular, right? But still, with a reasonable number of parameters, order of 10, say, you are able to reproduce the basic features of the deformation. So it's not that hopeless. It seems that the method is quite capable of approaching the complexity, geometric complexity.
Maybe a question not so related to our lecture today. Can you give us a basic simple command on the researchers who working in people who working in PE, partial precision, and by using PE, what are their problem or what are the difficulties in just what is the research hot point? Maybe still, as a student of master material science, this may be more interesting to me. What you told us is quite deep for me to understand.
Well, if I understand correctly your questions, where are the most challenging problems in PD approximation? There are so many. I think that perhaps one of the really critical points is the possibility of developing methods that are good for multi-scale. There are, of course, many methods for multi-scale. How do you combine multiple scales? And perhaps none of them are really very efficient so far. The challenge is to, from one side, to represent the physics, and from the other side, to end up with a method which is computationally feasible, computationally usable. And in some cases, this is has been done successfully. In other cases, it's far from being successful. For instance, just to give you a problem that is, in principle, relatively simple, flow in a porous medium, right? Which is a typical problem for oil engineering. You are far from having a method which is efficient and accurate for solving the simple Laplacian in a media which multiple scales in terms of porosity. If you solve, say, this equation is very simple to formulate, but very simple problem, but assume that this rho changes over very different scales, many scales. How do you represent it? Well, you represent it by multi-scale methods. And the typical approximation is that you want to create a separation of scales, the fine scale and the large scale. And then you have two different approaches, and then you have to have these two different approaches to communicate. But most often, cannot do that, cannot separate the scales, so there are a multiplicity of scales. So, this is a simple problem from the mathematical viewpoint. From the mathematical viewpoint, this is not a problem. If rho is bounded from above and from below, you can say everything about this problem. But you want to solve this by finite element, and you want to use it, for instance, parallel computing, because you're solving in a domain which is big enough, and you want to use a suitable precondition for this problem. This is far from being done. For instance, people are now striving to develop a coarse level correction for Schwarz for this type of problem. Right? So this is the example of a simple problem to formulate, which has a tremendous complexity from the computational viewpoint. Then you have problems which are much less simple to formulate. For instance, you have you want to go from the atomistic scale to the continuous scale, and through, say, passing from molecular Schrödinger equation, molecular dynamics, continuum models, and there the interplay between the scales is far from being understood. And people are working on that at the material level, for material science, for the biological scales, for the pure chemical models, and this is a problem that is there since at least 2 decades, and there is a huge amount of work to be done yet at that level. I would say that more in general, all the problem that involves the coexistence of different physical phenomena and different scales are very important at the, for the computational viewpoint. The example that I showed for the hard integration, you want to integrate the fluid dynamics, the deformation, and the chemical activation, and the electrophysiology. You have 4 different fields with different scales. This is also a nightmare from either from the mathematical viewpoint or from the computational viewpoint. It's a long list, unfortunately.
Okay, so I think we can conclude this second course, and let's thank Alfio very much.